somewhere.
Oh, okay.
Yeah, somewhere. So,
Oh, it's because it's in radians.
oh,
I got the wrong one.
okay, yeah. Yeah, make sure your calculator is in degrees, yeah.
Oh, okay, that makes sense.
Good. Oh, direction. What is the direction? Same, K hat direction. Yeah, K hat. Why? Well, curl your fingers from V to R. From V to R. That's this one. Now, you might want a formula that includes the cross product within it, so that you don't have to always find the magnitude and then the direction. So that might be also needed. So for a point charge, we can rewrite this formula. Oh, I forgot to mention, this law is called the Biot-Savart law. So it looks like this. So the magnetic field of a point charge equals to mu naught over 4 pi, and then Q, and then V cos R hat divided by R squared. Yeah, that's the magnetic field due to a point charge. Now, you may remember what the unit vector R hat, so there is sometimes it's useful to write it this way. Since R hat, a unit vector is always equal to what? You take the vector and divide it by its own magnitude, right? Mm-hmm. Right? If I want a unit vector, I have a vector A, and I want A hat. Well, A hat will equal to the vector A divided by the magnitude of A. So R hat can be written as R divided by R, like this. So if you replace R hat by R over R in here, the 1 over R, you will have an R cubed at the bottom. And here you will have V cross R. So equivalently, you can also write this. You can also rewrite it as V equals to R over 4 pi Q V cross R over R. It's not different formula, it's the same formula. I'm just rewriting it. Instead of V cross R hat, this is V cross R. Yeah.
That one is called VF Savart.
Yeah, it's just a different form.
Oh, the same thing.
Yeah, it's the same thing. And V cross R has a magnitude of V. Oh yeah, so the way we have it here. Yeah, this one also can be written as, if you multiply by R on the top and R on the bottom, you have R and then R cubed. The cross product always gives you the sine of theta. So the cross product of two vectors will be the magnitude of the first vector times the magnitude of the second vector times the sine of theta, sine of the angle between them. So in this case, the magnitude of the cross product will be the magnitude of V, which is V, the magnitude of R hat, which is what?
R vector overall.
That's the, how you calculate R hat, but its magnitude, how much is it?
R.
R? The magnitude
Oh,
of.
one.
One, yes.
Unit
The
vector.
magnitude of the vector R is R, but the magnitude of the vector R hat is
Oh,
called a
unit
unit vector, right?
Mhm.
It's a unit vector, so it has size 1 unit. Yeah, size 1. So the unit vector has size 1, so it would be the magnitude of V, which is V, times 1, so just V, times the sine of theta. So that's what you have here. V and the sine of theta. So this is the equation. This one is a result of that equation. But we started with this one because this one deals with just magnitude. Okay. And these two are equivalent, right? You might say there is an R cubed, but there is an R instead of R hat. Now, I was going to redo the problem we just did using vectors, but I think, let me just discuss the cross product of two vectors, how to calculate it. There is a definition of the cross product, and I will give you one that I use. It's equivalent to it. It is, you can take it as a definition. In the next worksheet, we will have some practice with the cross product. Cross products.
So,
Yeah.
so is this like more general than this? So is this just for point charge or are both of them for point charge?
Yeah, so this one is for point charge, it's moving charge.
Okay.
They're both for point charge. Cross products. So if you have a vector A, and you cross it with vector B, you get a new vector C. The magnitude of the vector C, we will write down the magnitude first. The magnitude of vector C is equal to the magnitude of vector A times the magnitude of vector B times the sine of the angle between A and B. So for example, if A is this way and B is that way, then this is theta. It's the angle between the two vectors. Alright? So how do you calculate the, so this gives you the magnitude. The direction, again, you can say use the right hand, but sometimes you want the formula that tells you exactly what it is without using the right hand rule. So you can write it this way. So vector A is AX I hat plus AY J hat plus AZ K hat. Vector B is BX I hat plus BY J hat plus BZ K hat. The cross product, there is a long formula that you can write it down. You don't have to memorize it. Here is how I write it, so I can remember. It looks like this. So if you have A cross B, write down the following. Write I hat, J hat, K hat, and then write the vector A horizontally like this. Without including the I hat, just include the what's in front of it. So you got AX, BX, AY, AZ. And then for B also, BX, BY, and BZ. And you want to find what's called the determinant of this. So the way I do it is this. Rewrite the first two columns and put them here. Rewrite the first two columns and write them here. So that I hat, J hat, so AX, AY, BX, BY. Okay? Then multiply this way. Multiply this way. So let's see what we get. We multiply that way. We will get this. I hat and then AY BZ. So AY BZ times I hat. And then this way. You get J hat times AZ BX. So plus AZ BX J hat. And then multiply these along this line. So you get K hat AX BY, so AX BY K hat plus AX BY K hat. Okay. Next, I'll draw them with a different color. Next, start at this quadrant now and go this way. But when you do it this way, left leaning, you have to put a minus sign. you have minus, so this one will be minus j hat ax bz. So minus ax bz j hat, so minus ax bz j hat. Oh, I forgot the subscript on this one. I think it's bx, right? For this one? Bx, right? Next, this one, so it's still a minus sign, because we're going this way. So I hat az by, so minus az by I hat, so minus az by I hat. I guess I forgot the bz here, right? Yeah, bz. Okay. And then k hat ay bx, so minus ay bx k hat. Okay. Now group them. That's it. That's the cross problem. Just group them together. The I hats together and the j hats together. So you get the following result. Get the following result. So aybz minus azby. I hat plus azbx minus axbz, azbx minus axbz, j hat, plus axby minus aybx, k hat. You can take this to be the definition of a cross product. In your top 3 book, I think they said this is the definition of a cross product. So I don't remember this. For some reason, I just can't remember it. Even though if it's I hat, that's the x, so here should involve y and z only, but I still don't remember. I think I'm just too used to this, and I don't need anything besides that. So, yeah, that is that. Now, there are a couple things you can do. For example, if I do the cross product of I hat cross k hat, what do I get? I hat cross j hat, sorry. The
I hat.
If I do this, I hat cross j hat.
Oh, okay.
You will get k hat. You will get k hat. Let's, for practice, let's do that. Okay. Can I erase these 2 boards? I want to do a calculation before we leave. I planned on 2, but. Okay. So, again, you can use your right hand. If it's just the unit vectors, just use your right hand. So here's the question. What is I hat cross j hat, right? Well, my first vector is A, so you can call this A, the vector A, and this is vector B. So, let's see what we get. I get I hat, j hat, k hat, but this vector only has the I hat component, so it's 1 I hat, nothing in the j hat and k hat. And this vector has just j hat, so it's 0 I hat, 1 j hat, 0 k hat. Now, repeat the first 2 columns. So I hat, 1, 0, and then j hat, and then 0, 1, right? Now multiply across. What is I hat times 0? 0. J hat times 0? 0. K hat times one,
K,
times one times one. So what do you get?
1,
One K hat, right?
K hat, yeah.
K hat. And then this way, J hat times one times zero,
0,
zero. I hat times zero times one,
K.
zero, right? Because you get zero. And then K hat times zero
0.
times zero, very zero. So just K hat. Okay, so just K hat, that's what you get. This is, I know it's an overkill, but you can do it, all right? So the way you can calculate the cross products, again, is I hat, here is J hat, and you're crossing I hat into J hat, I hat into J hat, and you get a vector in this direction, and here's K hat. And so on. If you want to do J hat cross I hat, what if you reverse that? J hat cross I hat.
J hat cross I hat minus K.
Yeah, if you cross this, yeah, you would get minus K hat, because it goes into the floor, if you reverse it. And it's a general property of cross products, A cross B is equal to minus B cross A. Cross product of two vectors. If you reverse them, then it's, you get a minus sign. And the vector they produce is always perpendicular to both of them. So, again, you can use this definition to prove that. You can say this, if this is, let's say this is vector C. Vector C is the cross product of A and B. However, if you do the dot product now, remember we studied dot product of A dot C, what do you get? Since it's perpendicular to both of them, dot product of two perpendicular vectors is
Zero.
zero. So dot product depends on the cosine. Yeah. And then if you do B dot C or C dot B, you will get zero again, right? Because it's perpendicular to both. And there are other like relationships with like A cross B cross C. Forget what there are different relationships that you can derive. Okay. Okay. So now, rarely you have not rarely, where you have just a charge moving by itself. We're usually interested, just like Oersted was doing an experiment with currents, right? A current that's moving. So a current moving is a bunch of charges that are moving. So what is the magnetic field due to a current? Right? What is the magnetic field due to a current? So the magnetic field So let's say I have a current in this direction. This is the current. Right? Right? That's the current. Going in the, let's say, to the right. Here's a portion of that current here. A portion of that current. And the question is, how much magnetic field does it generate a distance r away? Which is not. So this is, you can call it ds. Yes, the length of this segment is ds. And there's a charge dq moving. There's a charge dq moving. So I'm going to use the magnetic field of a point charge to derive this for the current. So for a point charge, if I have a charge q, this is the formula, right? What if I have just a charge dq? A small charge dq. So it will look like this. I'll write it as dv. Because I don't have a q, I just have a dq, so I'm going to write it in differential form, dt. So it would be mu naught over 4 pi, and then instead of q again, I would write dq, right? I'm looking at this formula here. Now, the velocity, right? The velocity, something is moving in the x direction, and the velocity is dx dt, right? So we don't have to be in the x direction, so I'm going to call it just ds dt. This vector is ds dt. So the velocity would be ds dt. Right? Again, that's the velocity. And then cross product with r hat divided by the distance squared, which is r squared. So ds dt, I'm going to write dq dt. I'm going to divide the q by the dt, not the ds by the dt. So I get dq dt. So look at this. What is dq dt? Huh? Current. I. Yeah, dq dt is I. So you get dv equal to mu naught over 4 pi. dq dt again is I, so that's the current I. And then ds cross r hat over r squared. So that's the magnetic field due to a small current segment. Now you never have just a little portion. Current's always part of a long wire. So that's why the next step is to calculate the magnetic field due to a whole wire. Start with a straight wire, just straight, no curves on it. And then we want to find the magnetic field due to that wire. And let the wire be long. In fact, infinitely long, so that the integral is singular. So that's the next step. I think we can do it. So current carrying wire. So here is the current, right, along the x direction. X, y. And let's say the point P is here. Now here is the y-axis. Let's say the point P is here. The distance y. This is the distance y. The question is, you have a current segment, so the current is this way, right? This is. Now you have a small current segment here. You have current segments everywhere on this wire. They extend from x equal to minus infinity all the way to x equal to what? Plus infinity, right? So here's ds. This is ds. In this case, ds, right? ds is in the direction of the current. Remember how we got ds? It was dv dt. I'm sorry, ds dt was v, so ds points in the direction of the velocity. So since the current is moving this way, then ds would just be dx times I hat. Right? It's dx, and it's in the I hat direction. Okay, now, what's the distance from here to here? Well, for here, this is x, right? This is x. And so the distance from here to here, so, yeah, let me write down what r is. So r would equal to, would equal to this. R would equal to, so the vector r points in this direction, right? This is the vector r. That's the vector r. So r has an x component, which is x, and it's so it's actually negative x I hat, and it has a y component, which is plus y j hat. Why does it have to be negative x, not just x? Actually, it's going to be positive. Yeah.
Oh, I was looking at the wrong one.
But x itself is what?
Yeah.
Is a negative quantity. So negative x will give you a positive quantity. Not that it matters in this case, it's going to go away. So if you have another current segment here, on the other hand, if you have it here, R will point this way, so it's negative. So, when x is positive, the x component is negative. That's going to cancel anyways, so we don't really care about it, whether it's positive or negative. Just to be accurate, that's what we have. Now the vector r, or the magnitude of the vector r, will just be x squared plus y squared square root. Okay? Now, I'm going to write this formula here. So dB is equal to mu naught I over 4 pi, and then I have ds cross r over r cubed. Where did I get this from? Now it has r squared, but it was r cubed.
You change the R, you make it.
Good, yes. The unit vector r hat is just the vector r divided by r, by the magnitude of r, so just like what we did earlier, right? So that's where this one is. Now let's first calculate this cross product, this cross product that makes life easier. So that cross product, let's first do this. ds crossed with r, it will be. ds is here, it's dx I hat. So you have dx I hat cross product with r, which is negative x I hat plus y j hat. Okay. Oh, sorry. Let me write my cross product then in different color, because my cross product looks like an x now, right? And we have the variable x, so cross product, this is the cross product, okay? That's what I'm doing. Maybe I should do that next. So the cross product, so you would have dx I hat cross product with negative x I hat. What's the cross product of I hat with I hat?
Zero.
It's 0, because remember, the cross product, the magnitude would be the magnitude of the
Sine
product
zero.
of the two magnitudes times the sine of theta. So if two vectors are parallel, their cross product is 0. So this I hat with I hat gives you 0. So, right, the cross product of the I hat with the I hat part is 0. The rest is 0. You multiply 0 with anything. Now the next one would be I hat crossed with j hat. This one. The I hat with j hat. So these two give me 0. How about these? What's this cross product?
K.
So I get, I hat cross j hat is k hat. So this will give me k hat, and then I have dx and y, right? So y dx. Y dx. Okay, that's what okay, so let's write that down. So we get dB is equal to, I'll put the k hat right in front of the equation because it's a constant. K hat is a constant direction, so it's good to put the k hat right here. And then I have mu naught I over 4 pi, mu naught I over 4 pi. And then this cross product just gave me y dx and the k hat. The k hat is already here, so y dx. Okay. And in fact, I'm going to write the y right here. So that's there. And then r cubed. What is r cubed? Well, this is r. So when you cube it, you get what? X squared plus y squared to the power 3 halves. Good. You get x squared plus y squared to the power 3 halves. 3 halves. Now we're integrating this from for the whole current carried wire. So minus, dx starts from minus infinity, or x starts from minus infinity and goes all the way to the end of the wire at positive infinity. So B so I need to compute this integral here. That will give me the result. And I need the other board, please. I need to erase the other board. I mean, at this point, I can be lazy and say, look it up, it's in an integral table. That's probably the easiest way out of it. But let's compute. So I'm going to erase the other board.
Suppose if you said if, looking at this table, this graph, you said if ds is on the other side,
Yeah, dx is here.
so then dx is positive,
Dx is positive, yes.
or sorry, x is positive.
X is positive, so, but the vector r points this way, right?
Yeah, it's gonna point in,
Left.
yeah.
So it would be negative x.
So the middle where it is given.
Yes, yeah. If x is positive, then it points in the negative direction. If x is on this side and it's negative, minus of a negative number will be positive, and it should point this. But in this case, again, the cross, it didn't matter. Where is, yeah, here it is. So, as you might guess, we'll do a trig substitution for this one. Do a trig substitution. Alright, so I would just take this part of the integral, this part, and then I will get the result and we will write it there. So I want this integral from minus infinity to infinity of dx over x squared plus y squared to the 3 halves. So we're going to say let x equal to
Some trig thing.
some trig thing, yeah. Let me remind you of this before I say let. So sine theta squared plus cosine theta squared is equal to 1, right? If I divide both sides by cosine, I will get tangent squared of theta plus 1 equals 1 over cosine squared would be secant squared of theta. So whenever you have something squared plus this is just a constant, can be factored out, and it would just be something squared plus 1. Something squared plus 1. So you want the tangent substitution. So I'm going to say let x equal to y times the tangent of theta. So first, this will have the consequence that dx will be y secant squared of theta d theta. That's the first one. So that's the first part. The next one is, let's square the x and see what we get. Put the start x in. Next thing is this. Next double star will be x squared plus y squared will be, but x is y times the tangent of theta, so squared plus y squared. That will give us y squared tangent squared of theta plus y squared, which is y squared times tangent squared of theta plus 1, which is y squared secant squared of theta, right? So we're going to substitute that. The integral becomes very easy. go here. We'll get to the limits in a second. Dx, we're going to put what?
Y secant square theta d theta.
Yep, y secant squared of theta d theta. And then, this thing to the 3 halves. What am I going to put for x squared plus y squared?
Y squared secant square theta.
Yep, y squared secant squared of theta. Now the limits. What does theta approach as x approaches minus infinity?
0.
So, so x is y tangent theta
I over 2.
minus pi over 2.
Oh.
Yeah. Again, remember the tangent, it looks like this. This is pi over 2. This is minus pi over 2. So, yeah, it would approach minus infinity as you approach minus pi over 2. So, you would go from minus pi over 2 to pi over 2. So, y, first take the square root, it just becomes y secant, and then cube it, right? The 1/2 means square root, so square root it, then cube it. So you will get integral from minus pi over 2 to pi over 2, y secant squared of theta, and then here you will have y cubed secant cube of theta, and you would have 1 over y squared, right? Y over y cubed is just 1 over y squared. Secant squared over secant cubed is just 1 over secant, so d theta over secant of theta minus pi over 2 to pi over 2. And so that's 1 over y squared cosine of theta d theta minus pi over 2 to pi over 2. What's the antiderivative of cosine?
Negative sign.
Sine. Derivative of sine is cosine. Derivative of cosine is negative sine. So in this case, it's just sine. So you will get 1 over y squared sine theta evaluated from minus pi over 2 to pi over 2. Now, sine of pi over 2 is 1. Sine of minus pi over 2 is minus 1. So to have 1 minus minus 1, which is 2. You get 2. So this becomes 2 over y squared. That's all. All that became 2 over y squared. So we're going to replace this by 2 over y squared and see what we get. So we get our k hat mu naught I y over 4 pi, and then that integral became 2 over y squared. So you get b, therefore will be mu naught I. 2 over 4 pi is just 2 pi. And then you got a y here and a y squared. You get y. And of course the k. So from now on, if you have a very long wire, this is the